In lecture 6, I'm going to introduce probability, this part 2 or the second part of probability. And specifically, we're going to discuss properties of continuous random variable and how to address the probability of them. Okay, so let's get started. So the first concept, very important fundamental concept I want to introduce here is called PDF, which is the short for probability density function. Okay, so probability distribution of a continuous random variable is expressed by its probability density function, lowercase fx. And fx is often represented by a graph or an equation. Okay, here we have three graphs showing you three PDFs. The first one is a straight line, right? It's a straight line. The second one, the curve of fx is a bell-shaped figure or curve. The third one, you can say it's a curve again. It's a curve again. And for this curve, when x increases, this curve decreases dramatically. Okay, and the value of PDF at any sample point on x-axis can be interpreted as providing a relative likelihood that the value of the random variable would equal that sample point. So it's not the value of fx is not probability. It's the density of probability. So what is density? Okay, so probability density versus probability. So density is per unit value of something. For example, in order to calculate the weight of water for a specific volume, we need to use the density of water rho to multiply the size, the volume of that water body, right? And raw water is a constant, is 1,000 kilograms per cubic meter, right? For example, there is a water body and the volume of that water body is 2 cubic meter. You multiply these two, you get the specific weight of that water, which is 2,000 kilograms or 2 tons. So this is how you calculate the mass or the weight of 2 cubic meter water. It's similar for probability density. Okay, similarly, PD or probability density is probability per unit value of a random variable, and it can be greater than 1. So probability itself cannot be greater than 1, cannot be larger than 1, but the density, probability density can be larger than 1. Okay, they are different. And PDF is the function for probability density instead of probability. Okay, so the difference between PDF and probability is very important. Okay, do not confuse them, do not mix them. Okay, so how to calculate probability from probability density? So according to the method we use to calculate the mass of water, we need to use something to multiply the density to get the actual mass. Similarly, we need to use probability density to multiply something to get the probability. How to do that? So the probability that the random variable lies between two values, let's just use A and B to address these two values, of the random variable is obtained by integrating the probability density function between these two values. In other words, when we have a PDF and then we want to know the probability of a random variable of the value of a random variable between A and B. In order to calculate that, we need to do calculus based on this PDF. So the probability of X being between A and B equals the calculus of Fx between A and B. So in this class, you don't have to actually use a pen to calculate the calculus of Fx between A and B. We use graph because calculus has very clear geometric meaning in mathematics. For example, here, we have Fx as a vertical axis, and for horizontal axis, we have the variable. And this solid black line is the curve for PDF. And C and D, they are the boundaries for this PDF. Okay, C and D, they are not that important here. Let's talk about A and B. We want to find out the probability of random variable X being between A and B. Of course, we need to use this calculus to get the result. But like I said, you don't have to actually calculate this calculus because the result of this calculus equals the size of this shaded area formed by A, B, horizontal axis, and the curve itself. So it means that once we have this curve and we can calculate the size of the shaded area, then that size of the shaded area is the probability you are trying to find. So the result of this calculus equals this shaded area defined by A, B, X axis, and the curve itself. So basically, it means that as long as you can draw the curve for the PDF, then you can assign two boundaries, A and B. Together, this curve, A, B, and the horizontal axis, together they will form a specific area. You can just shade it. And once you find out the size of that shaded area, you find the probability of X being between A and B. So of course, we have different shapes for Fx. Could be a curve like this, like a bell. Could be a curve like this, right? But no matter what, you should grab the core of this problem. You always want to find out the size of the shaded area, no matter how the shape of Fx changes. It could be a straight line, a flat straight line, could be a curve like this, could be a curve like this, could be curved like other shapes, but it doesn't matter. Find out horizontal axis, that's the bottom of the shaded area. Find out A and B, could be any values, right? So they are trying to define the range of this probability. And then draw the curve for PDF. And together with this curve A, B, and the horizontal axis, you will find out a shaded area. And the size of that shaded area is Px between A and B. Okay? So that's how we do this. Okay, we have introduced PDF. Now let's talk about CDF. CDF is simply the cumulative distribution function. Okay, CDF specifies the probability that the random variable X takes on a value less than or equal to X. So we use uppercase F to address CDF. So Fx actually equals P, which is the probability of X, uppercase X, equals or smaller than a specific X value or lowercase f. So we use uppercase F or CDF. For CDF, and the lowercase fx for PDF. So here is a curve for PDF. So lowercase f, right? So random variable x, and if you specify a specific value a, then the shaded area on the left side of a is used to address the probability that x equals or smaller than a. So if we compare this with fx, uppercase f, CDF, this is the curve of CDF, okay? Because it's cumulative. So as the random variable increases, you can say this curve increases continuously. Now, if we say we have another value for random variable and it's b, so this is the position of b in PDF. So where is b in CDF? Is here, right? So it is still on the right side of a, but because CDF is for cumulative probability, so you can say that the area on the left side of B continues to increase if you move B to the right side continuously. Okay, and in order to calculate, for example, the probability between A and B, of course we can get back to use PDF to calculate that, but you can also use CDF to calculate that, because FB, okay, of course, here is a CDF. FB equals the area, the shaded area to the left side of B, and FA equals the area to the left side of A. If we calculate the difference between them, of course, this area is the result of this comparison, right? This area is the difference between FB and FA. And you can say conveniently, this shaded area, the size of it actually is what? Is the probability of X being between A and B. This is exactly what we wanted. So you can use PDF to calculate this result, right? It's the shaded area, the size of the shaded area. And if you have a CDF, you can also do this. You just calculate the difference between FB and FA. The result is the same. You get the same result. It's still the size of the shaded area, right? Marked by these red lines. So usually we use more PDF than CDF, but you should know that if you have CDF, it's still doable to calculate the probability of the random variable between two constants. Okay, let's continue. So next, I'm going to introduce two types of specific continuous probability distributions. Okay, the first is uniform or rectangular distribution. The second one is more important. It's widely used. It's the most widely used distribution for continuous probability, which is normal distribution. So for the first one, uniform or rectangular distribution, an example would be like this. Suppose that the mean annual temperature for a location was uniformly distributed between 10 Celsius degree and 18 Celsius degree. What is the probability that the mean annual temperature is between 12 Celsius degree and 15 Celsius degree? Okay, uniformly distributed means that the probability of getting any value for that specific random variable stays the same. That's why it's called uniformly distributed. The probability of getting any value stays the same. Okay, for normal distribution, suppose that the mean annual temperature for a location was normally distributed with a specific mean and a standard deviation. what is the probability that the mean annual temperature is between 12 Celsius degree and 15 Celsius degree. Here, the probability is not evenly distributed. Actually, the PDF of normal distribution is a bell-shaped curve. Okay, I will show you that. But before that, let's talk about the relatively more straightforward one, uniform distribution. So the process of interest consists of equally likely outcomes. What's the formula? Of course, we still have A and B. The smallest possible value of the random variable. B is for the largest possible value of the random variable. And fx PDF is like this. If your random variable, the value of your random variable, which is addressed by lowercase x, is somewhere between A and B, this is the function, the formula of the PDF, the formula of the function. Okay, 1 divided by the difference between A and B, or say B and A, that's more formal. If the value of your random variable is smaller than A or larger than B, then PDF equals 0. So this is a piecewise function, which means that the formula of the function changes according to your independent variable, or depending on your input, which is x, right? So if we draw the graph for this function, this is a function, right? If your random variable is somewhere between A and B, this flat black straight line is a curve, and its value on y-axis is 1 divided by the difference between B and A. And if your random variable is somewhere smaller than A or larger than B, then the value is 0. That's why there is no curve you can see here, but the curve is there. The curve overlaps the horizontal axis because the value is 0. Okay, so this is the formula for uniform distribution. What formula? PDF formula. Okay, so probability on an interval. Okay, just assume that A, C, D, B. This is the rank of these 4 constants. The probability of x occurring between C and D is the value of what? Probability of x being somewhere between C and D. So A and B, they are boundaries. There are 2 boundaries for this stepwise function, right? If x is smaller than A, it's 0. If x is larger than B, it's 0. And what we care about is the probability of x being between C and D. And I have mentioned this multiple times, how to find out that probability. You find the size of the shaded area defined by C, D, x-axis, and the function itself. So what is the size of this shaded area? That size equals this p-value. Okay, so of course you can simply calculate the calculus here, and I would just ignore the process here because it's not calculus class. And the result is this: the difference between D and C divided by the difference between B and A. And this value equals the size of the shaded area, also equals the probability of x being between C and D. So easy formula for uniform distribution. Okay, for example, P represents the probability of x occurring on an interval, and you can simply use this easy formula to do that. Max and min, they are representing B and A, right? The max value for that PDF to have a value larger than 0, And A is the mean value for that PDF to have a value larger than 0. And for numerator is simply the length of the interval. The length of the interval here for this specific example is the difference between D and C. So numerator, D minus C. Denominator, B minus A. Then you have it. So it's just that simple. This is for uniform distribution, okay? Okay, let's just review that temperature example I mentioned before. So the mean annual temperature is uniformly distributed between 10 and 18 Celsius degree. So random variable X, the mean annual temperature. Okay, find the probability that the mean annual temperature is between 12 and 15 Celsius degree. That is, find the value of P when X is between 12 and 15. Of course, the unit here is Celsius degree. So easy formula. You need to find out A, B, C, D. A is the mean value for the stepwise function to have a value larger than 0. So it's 10, right? Because the annual temperature cannot be lower than 10 or cannot be higher than 18, right? Which means that if the temperature is higher than 18, then the probability of that temperature is 0. If a specific temperature is lower than 10, it's not going to happen, then the probability density function is still 0. So A is 10, B is 18, right? And what's the probability between 12 and 15? C is 12, D is 15, right? D minus A divided by B minus A, so that's it. The probability is 3/8. So easy formula here. The length of the interval is the difference between 12 and 15. Maximum minus minimum, 18 minus 10. Okay, so a uniform distribution is very straightforward and easy to understand. So it's also a good choice for the preparation for normal distribution. Okay, for normal distribution. It's more complex, but relatively. It's not very complex, but compared to uniform distribution, yeah, you can say it's more difficult to address. And I will stop here and I will use next video to finish this lecture. Okay, thank you.